Hi, this is Manuel Ramirez and Felipe Ramos, and we are going to talk about the Seismometer, that is a project for this class, Signals and Systems. So, sometimes, for the last few months, there have been a lot of earthquakes that have happened around the world, and Mexico also have several of earthquakes. So we decided to make a contribution to detect those earthquakes before you can actually think before you can actually think. So as we can see in the image in this GIF, the lady doesn't have any idea about an earthquake an earthquake is happening, but the man already knows. So sometimes we don't know if the earthquake is happening or not. So we are in our office or in our house hanging up, like chilling, and then an earthquake happens. So then first you don't know if it's actually an earthquake or not, and then if it is an earthquake, like you want to have like some time to try to run out of that building and take cover outside that, and very far away that building. So we decided to make this application. Well, nowadays everybody has a cell phone, everybody has this smartphone, and we decided to make this app, this alert, that it will pop up to your screen in your cell phone when an earthquake is happening or when an earthquake is coming. So this app is going to alert you. It's going to make sounds, very strong sounds, to make this alert.
We'll be explaining the functional block diagram of the seismometer alert. So first we got a piezo sensor, which will be represented like this. This piezo checks the vibration that we will have, and normally it's oscillating between 23 millivolts, so this will be the sign when it's not moving. Then when we have vibrations, it will can go to 0.8 volts, and in this range is when we will have an oscillation. Then the sign of the piezo will go to a comparator that will compare to a voltage that we will apply. In this case, we decide to apply 0.12 volts. So when the piezo sends more voltage than 12 volts, that 0.12 volts, it will send a sign that is high, that it's moving. So this sign will go to a microcontroller unit. In this micro, we are going to read the comparator, and then we will send the information we get from this to a modulator. So this microcontroller will function as a transmission. That's the transmission. Then we will have a modulator that is built with a transistor, and then with a timer NA555. So this This modulator is going to achieve the sign that is coming in this way, in binary. We'll start oscillating in when it's 1, it's going to oscillate in 600 hertz. Then when it's in 0, we'll be oscillating in 0.3 kilohertz. So we will be explaining the maths and the calc to get the frequencies you want with the resistance that are applying the circuit that we will see later. Then this will go to a demodulator, which we are going to build from 2 bandpass filters. This bandpass filter is going to check if it's a 1, and this is going to check if it's a 0. So we're going to take the frequencies we get here, the 600, and we will look for 550 and 650 hertz. So the frequency that is between these two range will be determined as if it's a 1. Then for this one, we're going to apply 1.25 kilohertz and 1.25 kilohertz. So if it's between this range, we're going to consider it as if a 0. Then we're going to apply a diode that will function as a half cycle rectifier. In this case, it's going to be also a diode. And then we're going to apply a low pass filter. In this low pass filter, we're going to check the frequency of cut for the frequency that we are sending the data. So we're going to design that filter to that frequency, the one that we are sending. And then we'll go to a comparator, both sides. And in this comparator, we are going to get the sign as we were sending it. So it's going to be like that. And then we can apply it to another microcontroller unit that is going to be controlling a BLL. And we bought a Red Bear BLL low energy Bluetooth shield. So the microcontroller will be controlling this. And then we design an app for iOS in Xcode. So this is going to send it to the cell phone, and it's going to send the alert when it's sending a high signal, which will be the Seismometer. Thank you.
So we were searching about how does an earthquake is detected. So for a long time in the human history, there has been this seismographer that when the earth moves in this movement, we can say in the axis, this is the sensor. We can say this is a sensor, and this ball is writing in this paper. So when there's a movement of the earth, everything but the ball is moving. So when it's moving, the the ball is like kind of writing in the paper, and we can see that the earth is moving. And nowadays we have the seismometer, that is the same as the other one, that is this sensor, that is something is moving, like physically is moving with the earth. But in this case, well, for example, in the other case, the seismographer writes in paper, but the seismometer writes, well, doesn't write. It is recording like digitally in a computer. So all the information about the movement of the earth is transferred to a computer. For researchers to take a a very deep uh, investigation about the movement of the earth, they amplified first the signal of this output. They magnify, they amplify the signal, and then they can uh, make sure how does the earth is moving, or like a very deep information they can get amplifying the signal. But we are not going to make that an amplification of the signal. We are only try to make only when a very strong movement is happening to make an alert. So we didn't take a seismometer, so we are going to make a seismometer. So with this is a piezo element, that is a very thin film, a very thin plaque, that when it blends is going to take out some voltage in sine form. Well, not in a very good signal, but it takes this we can say this analog signal, and when this vibrates, we're going to transpass it to a comparator. For example, we are going to make, well, the voltage that comes out of the piezo element when it's blend is around 200 and 800 and 1000 millivolts. We are going to take that range to take the comparator, and when the sensor reaches this voltage, they're going to take this signal, that is some pulses. And then, well, Pipe has already explained it, or is going to explain it. And then this is going to go to an Arduino, and then this Arduino is going to transfer this signal to a modulator, and the modulator, and then they're going to go to another Arduino and going to display the information to the cell phone. So this is our objective. We are going to
So for the electrical design of our project, we have this diagram that shows all the system. So we're going to start with the piezoelectrical sensor that is represented by this. This is connected to the positive side of the piezo, to the pin number 2 of an LM311, that is a comparator, a voltage comparator. This integrated circuit is connected to 5 volts in his 8 pin, and to minus 5 volts in its 4 pin. It's connected to ground in pin number 1, and in pin number 3 we have connected the voltage that is the limit or the start from where we start taking, that is a seismo. So when the piezo sends over this voltage, when the voltage of the piezo it's bigger than this one, we start taking the seismo alert. So this is connected to a potentiometer that it's of 50 kiloohms, and well, we decided to apply this voltage. Then in the pin number 7 is the output, which is connected to a pull-up resistance of 1 kilo ohm, and also the resistance is connected to 5 volts. Then the output of the voltage comparator, it's taken to the microcontroller unit. In this case we were using an Arduino board, Arduino 1. So we have the pin number 0 of the digital pins as the input, and the digital pin number 3 as the output. So it's a very simple program that this microcontroller do, that we are going to explain later in the codes. So from pin number 3, the digital pin number 3, we take the signal and it goes to the modulator, which is this part. So we have the signal that comes from here. It comes from here, and this signal passed through a resistance of 220 ohms, and then it goes to a transistor, a PNP transistor. In our case we decide to use a BC 327 transistor because it was the one that we get from our city, and it was not expensive. So but any PNP transistor is useful. So the pin number 3, so taking like this is 1, 2, 3 in a transistor, this goes to a resistance that a potentiometer that is of 50 kiloohms, and then it goes to the pin number 7 of a timer, and 555 timer. It could be LM555 or NE 555, what you get from your store. So this pin number 1, it's connected to 5 volts. Then we have also connected to 5 volts another potentiometer of the same value, and a resistance in series, so it's adding up of 100 kilo ohms. Also connected to 5 volts is the pin number 8 and the pin number 5 of the 555 timer. This is connected to the other potentiometer and goes to pin number 7. Then we have another resistance, that is this. It's 47 kilo ohms, and it's connected from pin number 7 to pin number 6. Then we have a bridge, just a buzzer, just a simple cable from pin number 6 to pin number 2. From this pin number 2 we have a capacitor of 0.01 millifarads, and it goes to ground. And it's the same from pin number 5, sorry, and also pin number 1 goes directly to ground. Now this is the modulator part. from this part we have a digital sign that goes 1 and 0 in a frequency that we send the data of in 150 hertz, so it goes here. So now we have a modulated sign that oscillates. Well, I'm gonna tell it later. It's around 690 hertz and 1300 hertz. We will see later the calculations. So this modulator signal goes to two bandpass filters. So these are biquadratic filters, and you can look in internet, or well, these are the ones. We will show the calculus later. So we have we used an LM325 integrated circuit that has 4 operational amplifiers. We are using 3 and 3. So this is the high pass filter, the band pass filter, and the low pass filter. These resistance are to 1 kilo ohm, and these capacitors are chosen by the amount of the frequency, and this it's calculated by the quality factor of the filter. So why we have 2 of them? The question is, you might have that question. The answer is simple. So this is for when the output, when we are sending a high signal, so it's modulated in 69 in 690 hertz. So this is the sign for it, and this is the sign for when the signal is low and it's oscillating here in 1300 hertz. So we take the output of the bandpass filter, that is from here and also from here, and we use a diode as a half cycle rectifier. Then it goes to a low pass filter designed to the speed or the frequency that we are sending the data. In this case is 150 hertz. So we have a resistance in both of them of 1 kilo ohm and capacitance of 1 microfarad, and this capacitance goes to ground. And then to finish to demodulate the signal, we use a comparator. We use another one, LM311. So we connected similar to what we have here, 5 volts to pin number 8, ground to pin number, in this case we connect ground to pin number 4, and ground to pin number 1, this filter to pin number 2, and this one to pin number 3, and from pin number 7 we take the output. It's also connected to a pull of resistance and 5 volts, and this goes to the receiver of that will be a microcontroller unit, and this microcontroller unit will have a Bluetooth low energy shield that allow us to connect to iOS cell phone, which are going to be Apple cell phone. So now that we have seen the whole diagram of the system, the electrical diagram, we're going to see where the values of the resistance and capacitance come from. So first we're going to check on the modulator, that is this part. So what we are looking for is the frequency of the modulator. So we are going to have two cases. The first case, it's when the signal is high. When it's high, it represents a seismo, so an alert that we are going to send to the application. So the formula for this case, it's the 1 over 0.45 over R1 plus 2 times R2, this times the capacitance. So as you see in the modulator, we have the important resistance are this, and the summation of these two. So this potentiometer is going to be R1, this resistance is going to be R2, and this potentiometer plus this resistance, it's going to be R3 in our formulas. So in this case, we decide to put around 20 kiloohms in our potentiometer of 50 kiloohms. So this plus 2 times 47, and then multiplied by our capacitance of 0.01, we're going to have a frequency of 690 hertz. And then for the second case, which is when the signal is low, and this represents that we are having a normal state or we are not having an earthquake, it's the same. We have this formula that is 1.45 over the parallel of the resistance 1 and the resistance 2 plus 2 times the resistance 2, the resistance 3, the parallel of resistance 1 and resistance 3 plus 2 times the resistance 2 plus our capacitance. So it's pretty much the same. The only thing that changes is the parallel. So we decide to put the other potentiometer at 40 kiloohms and adding with the resistance of 100 kiloohms that is in series with it. We have 140 kiloohms plus the other potentiometer that it's the same as this. So we have that is oscillating in 1.3 kilohertz. So remember these values. We also have low pass filters that are right here, this one and this one. This potentiometer, these low pass filters are designed to the frequency that we are sending the data. In this case, we decide to send the data in a frequency of 150 hertz. So the formula is this. The capacitance is 1 over the frequency that we are sending the data times 2 pi for the case of resistance of 1 ohm. So we get that the capacitance is 1 microfarad. Then we change the value of the resistance to 1 kilo ohm, and so the capacitance changed to 1 millifarad. And finally we got the bandpass filter that it's this one. We have as I said before, it's a biquadratic filter, so the values of all the resistance, and not including this is important, the value of these 4 resistance, it's going to be the same. These 5 resistance, my bad, is going to be the same, and the value of this capacitance also is going to be the same. For the calculations, we're going to have 1 ohm, and this resistance we're going to give the name of the resistance Q, and later we'll see why. So we have remembering that for the case when we have a high signal, we have this frequency. So to design our bandpass filter of this sign, that is the high, we're going to put this range. So it's 677 and 702 Hertz. So our frequencies between them. We're going to have a bandwidth that it's the frequency high that we decide here, and the frequency low that we decide here. It's this minus this times 2 pi. So we have that the bandwidth it's 50 pi, and for the cutoff frequency we have this formula that is 2 pi times the square root of the summation of the frequency that we decide as the range of our filter. So we have this is our cutoff frequency, and we also have the quality factor of our filter, that it's Q. We have a formula that is WC over the bandwidth. We substitute and we get that it's 1.5, so we can say that it's around 2. We approximate it to 2. So for a resistance that is 1, we have that the formula it's the same capacitance 1 over, in this case it doesn't see, but it's this frequency, the cutoff frequency. So this value goes here, and we calculate the capacitance that it's 0.26 microfarads, and the resistance Q that, as I said, it's this one and this one. It has the name because of the quality factor. The formula is 2 times Q minus 1. In this case our Q is 2, so we have a resistance of 2 ohms. So now we change the resistance to 1 kilo ohm, and also the capacitance change to 0.26 millifarads, and the resistance stays the same. And for the case of the low signal, we're going to design another filter that will let pass frequencies between this range. So our low range is 1288 Hertz, and the high frequency it's 1312 Hertz. So we use the same formulas. We get that we have a bandwidth of the same, and our cutoff frequency now it's 320. We have a quality factor of 2 also, and we start designing. So we said that our resistance is 1, then the capacitance is 1 over the cutoff frequency, as I said before. In this case it does see the value, So we got that the capacitance is 3.12 microfarads. For the resistance Q, we get the same value, and we perform the same transformation. So we have now a resistance of 1 kilo ohm and a capacitance of 3.12 millifarads and the resistance Q. So for the first Arduino, the code is this one. As you can see, it's not a normal code of Arduino because we are using a Atmel Studio. So if you didn't know, the microcontroller is not Arduino, the brand. The microcontroller, it's an Atmel microcontroller. So we are using the software provided by Atmel to program this Arduino. So it's called Arduino Studio, and we are using the assembler of this system, of this software. So here is the as in C++, these are directions and that are needed to be provided, and this specific is the vector of the interruption number 0. And then we enter to the first loop, that is the main one. We set the stack values to the highest and the lowest of the memory. Then we configure port D as an output and configure port B as an input. If you want to search for more information for the ports, I suggest you to look for the Arduino configuration where the ports and the pins are explained farther than the simple one. So and this is the configuration for the interruption, that it's going to happen when we have a rising edge. So in our case, we will be having a low signal that will go high when the Seismo starts being filled. So this interruption is going to set the output pin, and it's going to stop the normal code of the Arduino. So this one is to set up the interruption, and this one is to tell the Arduino to enable all the interruptions. If we don't do this, the Arduino or the microcontroller in this case specifically is not going to set all the interruptions. So these are the configurations needed to set up an interruption in Atmel. Then we will have this cycle. So this is the code that is normally executing. It reads the pin and it transfers it to port B. But this is only going to happen when the interruption happens. So when the input pin passes from low to high, the interruption will stop the normal cycle and we'll start doing this, that is basically reading it, and then we'll send it to the port D, that it's where the output is. So here we'll be sending to, in this case, the programmer set a buzzer, but in our case it's also connected to the modulator. So this is the flux diagram of the code that I previously explained. So it's basically we set up the the input as a port, and the input which will be the port B, and we set up the output in port D. We also set up the interruption in 0, that it's a feature that the admin has, and these are the part that explained it earlier. And then it goes to the main cycle, which is read port D, and it stays rating and rating and rating as long as the cycle as long as the input stays low. In the moment the input or the port B gets high, the interruption happens and it goes to the ESR, which stands for Interruption Service Routine. In this interruption service routine, or ISR, which it does, it transfers the information for the port B to the port D, and it sends the output to the port D. The moment it sends it, it goes over here to the main cycle. So it will be an arrow right here, and it starts rating and rating when until another high signal happens, and it goes this way. So now we have here the code of the second Arduino, the receiver. Remember that this Arduino has the Red Bear Bluetooth low energy shield. So it's a very extended code, so we're going to see it only the points that I think is important to see. So as you can see, it's very extended, because well, you have to set up the pins and also set up the shield, as you can see here. So and also the application has important influence here. You can see that the pin can have different modes and different states depending on the mode. So for example, well, here we have the setup of the shield, and then we have for example, we have here the pin mode is set up as an input, and we are telling this pin that it starts as a low. So in the application we will have a normal input, it will be normally in low, so it will detect a rising edge. As we go on, we could see that the pin has different modes. It could be a pin, we have here, it could be a digital, analog, a PWM, or a servo that we can attach and control with this code to an application. We are not using it, but it can be done. So this program has different cases for in order to not to crash. For example, we have here the mode of digital read, so it's working as an input, and it can read it, and it reads information that it's digital. So yeah, it also an important thing is that it checks if the BLL is connected or not. So well, this is important due to the application of it.